So today we are going to talk about the characteristics of the diode laser. Last week we discussed the coupled ray equations in the diode laser, especially one for carrier and one for photon. But it haven't comes out how the Li curve looks like. So this week we'll start with the Li curve of the diode laser and the speed of diode laser, because the high speed is the core of the modern telecommunication technology. And we will talk about what happens if the output power of the diode laser is really high. What phenomena we might observe with a high power laser diode, and some method to evaluate the parameter in the diode laser. So here's the brief review. Last week we said that in the diode laser there will be two coupled equations. One is for the carrier concentration, we call the dN over dt. And the second one is the concentration of photons. So we call the NP with P in the subscription. Alright, so we know that what's the threshold condition mean? Threshold condition means the population of the electron and the carriers are in steady state. So means the dN over dt and the dP over dNP over dt should be 0. And by that time, the everything, the carrier density and the current will be under its threshold value. So we have a pH in the lower split. And because the gain clamping phenomena, while your current is higher than your threshold current IPH, the carrier inside the cavity doesn't increase. It will be peak to the threshold current carrier density. So if there's no cavity, then there's no lacing, and the carrier concentration and the I might be having something like this. But now we have a cavity, and the criterion of lacing is the chip. So when I reach ITH, it is at the edge of the lacing action. And after that, all the carrier concentration will be turned to a specific value. Because the gain, the optical gain, is a function of the carrier concentration. So if we have a cavity and the cavity laces, the gain also stops at somewhere. And the slope here, the dG over dt, we call it differential gain. Okay, so we can start from here. If the system is under threshold current condition, that means delta I divided by QV minus NTH over tau, and minus the BG NPGH is 0. So this is the trend of gain, and this is the carrier loss. Okay, since it's still at the threshold level, the photon density haven't increased yet. So we can roughly assume at the threshold current condition, we can just let NP equal to 0 as a reasonable simplification. Then we can have the threshold carrier concentration divided by tau, since this term don't exist now, equal to delta I ITH divided by QB. Alright, so we can put this term back as the one at the left side. So the differential equation above ITH should look like this, because we already replaced this value. And when I larger than ITH, the N doesn't increase. Okay, because the gain clamping phenomena. So the NTH divided by tau can be reduced to the minus 10 in the first bracket. Then the stimulated emission term remains. Alright, and after lacing is still under steady state. So dN over dt should be 0. Alright, so we can simplify the photon density as this equation. because we just put the second term to the other side and divide it by VGGH. Alright, so the photon density at a specific current above lacing could be written as zeta I times I minus ITH divided by QVGGTH. So, okay, it looks a lot of terms, but we can still keep doing some simplification. Since it's already it's under a lacing, under lacing, so the gain is clamped. So zeta GTH, this is the modal gain, shall be its total modal loss. Alpha is its internal loss. Alpha n is the mirror loss. Means or we have another way to describe that. Alpha bracket I is the photon loss inside the cavity. Alpha n is the photon loss outside the cavity. Because while your photon is like hitting in the wall, bouncing around you, some of them will vanish inside the cavity. Some of them will leave the cavity. So you can measure that. If there's no photon leaving out the cavity, you will measure nothing. So the lacing cannot be confirmed. Okay, so this term will be equal to 1 over Vg over tau p. This is the equation from the Ray equation of photon. Then, with this Ray equation, we can simply write down like that, 1 over tau p, because we can times Vg to the other side. So 1 over tau p will be Vg times alpha plus alpha n. Because the tau p is the photon lifetime, so 1 over tau p means how many photons will be lost from the cavity. So it will be Vg times alpha. So you can see the first term means the photon loss, because this is the group velocity. Its unit is because it is a unit of speed, so that will be distance divided by time. Right? No, Vg is divided by time. And the alpha is in the unit of the distance, minus distance. So the whole unit, 1 over it is 1 over time. So it's still in the level of in the unit of frequency. Okay. So the first term will be how many photon loss inside the cavity due to the absorption. And the second term, Vg times alpha n, is how many photons will lost due to it leaves the cavity. That's the output power you will get. Okay, so we can calculate that what's the output power. It can be reduced as the first term is NPVP h mu. This is the photon density times its volume. So this is the total photon number in the cavity times h mu. So it becomes the total optical power in the cavity times the second term, the rate of photon leaving that. So that's the output power you will get. So the P can be written as the two terms like this. Then you can substitute the NP here with the Ray equation here from the Ray equation of carrier. Okay, put it back and let tau is equal VA over VP. VA over VP means while we are calculating the confinement factor, the definition is the volume of the E squared over dV and the active region E squared dV. And this means the mole volume of the active region. This is the mole volume of the whole cavity. So the numerator is the volume, the more volume in active region. This is the more volume of the ball cavity. Okay, so you can replace gamma also inside there. Then the output power is simplified as P is equal to zeta I injection efficiency times alpha n divided by alpha plus alpha n times H mu over Q times I minus ITH. Remember, this is only valid for I larger than ITH, or you will get a negative value of the output power, which is physically irreasonable. Okay, so how do we read that? When the current is assessing its threshold current density, the excess value is all transferred into the photon energy. Yeah, because I minus ITH divided by Q means how many carrier, excess carrier is injected. Times H mu means the carrier is transferred into photon energy. And you have the zeta I because some of the carrier might not inject into the active region. And then what does this term mean? Because when the photon is low, will partly due to the absorption, partly due to the cavity. So this rate is the portion of all photon loss to the observable photon loss. Okay, so P is equal to this term. It will be a linear term to your current density. So you can define something called the differential quantum efficiency. That means the P divided by H mu. How many photons you can measure in a differential way? Because now we want to only know the part after lacing. Now we need to do dP over the H mu. And this is the carrier injection, I divided by Q. Okay, so that means this term will vanish. And because it's I, so this term also vanishes. So the differential efficiency will be zeta I times alpha n divided by alpha plus alpha n. So that will be the slope of your the Li curve. Okay. So after lacing, there's something called the slope efficiency. If you count the power in, you need to times the photon per Q. So in this case, if you times that, the slope will be watt per amp. But if you're only counting the differential efficiency, it is per photon over per electron. So that's the only different value of the unit. So this term will be lambda divided 1240 divided by lambda. Alright. So you know there's a slope starting from ITH and start increasing like this way. Alright, so what happens if we consider the part below the threshold? Because if it's below the threshold, what will be neglected? Will be, because in this term we neglected let me see. After lacing, we neglect this term. We neglect the spontaneous emission. We neglect the spontaneous emission. But before lacing, we will neglect the stimulated emission. So the whole term becomes this way. We just replace the gain to the spontaneous emission part. Gamma beta SP times RSP. So we can repeat the whole procedure again and derive the LED part or the part before threshold also has a slope. Its slope should be H mu over Q, percent, zeta I injection efficiency, radiative efficiency, and the beta SP. Why? Because while we are talking about measuring the lacing intensity, we only care about the intensity of a specific wavelength. In the LED, there is a wide spectrum, and there are so many more. But while we are calculating a plotting like this, we only care about one of the wavelengths, aka your lasing wavelengths. So not all spontaneous emission is contributing such emission. So you need to time to beta SP to extract the interested mode out of the equation. Alright. So if you compare the equation, actually that's pretty similar. The only difference is the beta SP here. How many more is actually contributing your laser action? So for a large cavity, for example, edge emitting laser, the length might be few hundred microns long, but the wavelength is less than 1 micron. So the beta SP is very high, is very low. So for large cavity, the beta SP might be 10 minus 4 to 10 minus 5. For micro cavity laser, because the cavity, your size is very close to your optical wavelengths, so the number of allowed mode is less. So the beta SP probably only minus 1 to 10 to minus 2. So for large cavity, the slope of this part will be very significant. If this is 1 minus 4, that means the slope of this part is only 1 minus 4 times of the slope after lasing. So it will be show a very clear change, something like this, and this part is almost flat. So this is P and this is I. But for microcavity laser, probably this is only 1/10. So the transition here will be not so obvious. It might look like this. It is P and it is I. So it might be a little weak first, but you will see something like this. The transition will be smoother. So if the very special case, what about beta SP is equal to 1? There will be no difference between the spontaneous emission and the stimulated emission. It might be something like this. So that would be a very scientifically interesting work. Can we make a cavity so small and there's only one mode inside the cavity? Simultaneously, it hits the gain spectrum of your semiconductor. That will be a thresholdless laser. So that would be also a very hot topic for some group doing the microcavity lasers. But that will be not the scope. But if you are interested, this might also be your topic for your final report. Okay, anyway. So let's see what the spectrum will look like in the different stage. While the injection level is still low, the cavity effect will be very weak because the light before hitting the first wall will vanish. You are also observing the original intensity profile of the EL. So it will be a small profile like this. But while the intensity increases, it is approaching the threshold value. Some of the photons will start to run a round trip and be pretty close to its original value. It's called constructive interference, 建设性干涉. But some of the wavelengths is not. They will be destructive with each other because the round trip is not 2 pi, it's pi. So it makes some wavelengths has the much stronger photon intensity, but some of them is much weaker. So you will see something like a comb structure, like this. And all these peaks are the optical mode allowed in such cavity. But it's still the enveloped by its original spontaneous emission spectrum. So you might see one envelope and the second envelope for the high envelope is for the constructed interference. The low envelope will be the destructive interference. Okay, so that's what happened near lacing. But however, because after lacing, probably only one or two peaks is reached the lacing condition, gain is equal to loss. So let's add something here. So okay, this is what happens. So this is the probably gamma G, and this is the lambda. And your loss level is here. This is your alpha I plus alpha M. So when you inject, while you are trying to inject more carriers, but this point, this wavelength already reached threshold current density. Can you make the whole spectrum further increase? No, because the gain clamping phenomena, the spectrum will fix like this. But for this wavelength, all the excessive carrier will be transferred into the wavelength of this mode. So after lacing, only the one or two, because while the mode is so close, probably you will get 2 or 3. Anyway, only a very small region of the wavelengths will keep increasing with your injection current, and the rest of them will be kept in the same level or even suppressed, because the dominant lacing mode eats all the other carriers from other wavelengths. So after lacing, the spectrum will look like this, and probably you can still have a very weak background of your spontaneous emission. Alright, so while you are doing the relevant also at the beginning, you will be very intriguing process. So while injection your carrier little by little, you will see the spectrum increase, and the few peaks start appearing, and the one goes out. And if you record the intrinsic wavelengths, you will get a intensity current curve with 2 slopes. Then you can continue your characteristic. That means you successfully make a semiconductor diode laser. Alright. Since the fabric pro low laser, there's a 2 mirror. So that means your optical profile is hitting bounce back and forth in such cavity. There will be some loss from mirror 1 and some loss from mirror 2, because the R2 is not 1. If one of the R is equal to 1, that means there will be no energy detectable from here. So when the R1 is not equal to R2, how many the light will be extracted from both sides? Definitely you need to times a fraction of F1. That means because while you are doing what's your calculation here, only cares about the total energy leaving a cavity, but that doesn't tell you how does it leave, where does it leave. Okay, so while you are measuring your laser from a specific facet, you need to further times a fraction to obtain the real value. So how do you know what the F1 is? And that we will teach you in the next week. But we can have some simple conclusion. First, if we consider a symmetric case, R1 is equal to R2. The reflectivity of both sides is the same. That since it is symmetric, definitely the portion of light leaving from 1 to 2 should be equal. Then the F1 is equal to F2 is equal to half. And another special case is that one of the mirror reflectivity is very close to 1, but the other one is not. For example, R1 might be 0.995 after stacking so many layers of your DPR, and R2 is still 0.4. Okay, so in that case, the light leaving from mirror 1 will be very small, and most of the photon will leave in the cavity from the mirror 2, since only 40% of the field will be reflected here. Then in this such case, the F1 will be almost 0, and the F2 will be almost 1. But what happens in current for VSO? It might be R2 will be 0.995 and R1 is equal to 0.99. Okay, so they are all pretty close to 1. So how to calculate F2 and F1? We need to do with the transfer matrix. So we will see that next week. So you can remember a two spectral case for your homework here. This one is that the reflectivity of both sides is the same. Then F1 is equal to F2 is equal to the 1/2. The other is one is almost 1 and the other is not. Then the one with almost unity reflectivity will have 0% of light coming out from here, and the other side will get 100%. Okay. Now this is good enough for you to know here. Okay. So if we find a paper, it calculates. So this is really a paper I find from Applied Physics Press. This is not my data, it's some people other data. And now the professor asks you to extract what is threshold current density. If he forgot, the paper forgot to tell you. So the first thing you will find, it will definitely have a 2 slope. And probably you will reduce it later anyway. You can find a small segment of the second slope and do a direct line to try to fit that and see where it collides with the bottom axis. This will be your threshold current density. So it is not this point. It should be something like it's tracked back to the here. This is the more precise one. But for most cases, these two slopes is pretty different. So this point and this point probably no big difference. But for the equation, it means the points at the intersection of P is equal to 0. Second, if you have a slope here and the slope here, probably you can, if you trust the precision of this paper, you might get a few points here, get one slope. Few points here at such slope, and you can divide the difference of the slope. You will get the beta SP. Okay, and the third, the slope in the milliwatt to milli-amp. So this is watt to amp as well. You remember this slope will be, you can address this slope, and it will be F1 times theta d times h mu divided by q. So this value it can be evaluated by isolation wavelengths. F1, how much is F1? You need to read it carefully to know what's the reflectivity of both sides. Then you can extract the ZD. Differential efficiency can also be calculated. So that will be something like here.